Hello everyone, welcome to AriserTalent. I am your maths faculty Arpita Sharma. Students, we are discussing circles, right? And in our this new chapter, circles, what and what points we have considered. Okay, so we have gone through the terminologies used like center. Okay, here's the center, then the circumference. Okay, the next one was non-intersecting line. Okay, then the tangent. When the non-intersecting line touches the circle, it became tangent. Then the second, okay, when it is intersecting not one point but 2 points. Then chord, when the line becomes the line segment here, then we will call it chord. Then the minor arc and major arc. I have told you this minor one, this circular path is what? Minor arc, and this major one is major arc. Okay, so we have gone through this also. Now, next was sector. I have told you the example of pizza that this is what we call sector. Then segment. I have told you if you are joining 2 points. Now, what is the difference between chord and segment? That the complete part, this complete part will be known as what? The segment. Okay, but that only line was known as chord. Okay. So, here we'll talk about tangent because this particular chapter circle is, having a circumference of tangent in it. Okay. So, if I am telling you in this diagram that I am having a line PQ, okay, I am having a circle and I am having a line PQ, okay, what do you call it? Secant. Okay, so this is not passing through center, let the center be here. So, it is not passing through center, don't misunderstand it, it is secant. Okay, now you will draw a parallel line to this PQ line. Okay, then again draw a parallel line. Similarly, you will finally be having this line which is one parallel to PQ and second tangent. Also, a tangent I have told you, tangents what? Which intersect it only at one point on circumference, not at 2 points. So, can I say this that this particular tangent or any tangent in the circle is what? Nothing but a secant, specific secant. Okay. And here also, if you go this side, you will find this line, let it call as P dash Q dash, and let we call it like what? P dash dash and Q dash dash. This is the method we use all the many a times. Okay. So, what I am saying that this upper side I am having a tangent, this lower side I am having a tangent. Now, another tangent possible here with this line parallel? No. So, what you conclude that at most 2. What? At most only 2 tangents can be drawn to a parallel secant. Okay. Got it clear? Right. Now, if I draw this line, so what will you say? You will see that you will be having, just suppose it like AB and mark it A dash B dash. So, you will be having this line parallel to this and also the tangent. Now, again this. So, only 2, at most 2 parallel lines can be tangent in a circle. Clear? Okay. So, students, we have concluded some points here. What is tangent? Tangent basically came from a Latin word which means to touch. Tangent, to touch, it is known as tangere in Latin. Okay, now who gave it? Introduced by Danish mathematician whose name was Thomas Finneck. Okay, Thomas Finneck gave this concept in 1583 students. Okay, Now it's saying not this, but we have gone through this and we have concluded that tangent to a circle is a line that intersects the circle at only one point. I've told you, right? Then tangent to a circle is a special case, okay? Special case of the secant, okay? When the two endpoints of its corresponding chord coincides, right? This point, when the two endpoints of a corresponding chord coincide, is what? We are having this chord, okay? Now, this and this will coincide on this, right? So, it will make what? A tangent. Now, some points about tangent, that there can not be, again I am telling you, not be more than two tangents parallel to a secant. We have discussed it in the figure. The common points of the tangent, the common points of a tangent and the circle is called the point of contact. Means what? Here, if I am telling you this is the point where this circumference and this tangent touches each other. So, what is this? The point of contact of the tangent and the circle. Okay. So, here we call it the common point of the tangent and the circle is called the point of contact, and tangent said to touch the circle at the common point. Okay, students. Now, the first theorem is here. I've told you that the tangent at any point of a circle is perpendicular to the radius through the point of contact. You have to prove this theorem. Okay. So, first we'll draw a circle, right? So, can I have this circle over there? Right? Okay. Now, students, it's saying that any point of a circle is perpendicular to the radius through the point of contact. Now, radius. So, I'll be having a center here. Let it call O. Now, I'm having a tangent here. This is tangent. Why it's a tangent? Because it stretches up this circumference at a particular point, this point of contact. And now, what I'm doing, I am joining this point O. Let it call P here and Q here. So, I am having a line PQ and I am having this line, this point O meeting the line PQ at some point, let's say A. Okay. So, now what I have to prove? I have to prove that this OA is perpendicular to PQ. Now, first thing, how will I prove it? So, from a point, from any point, right? From any point, if I am having a line, so the shortest distance will be what? The shortest distance will be the perpendicular to the line, right? So, I will use this concept in this. I will prove somehow that this OA is what? The shortest distance between this PQ and O. If I prove this, then this is simple. This simply can be proven that O is perpendicular to PQ, right, students? Okay, so let's do that. So, parting it here, given what we have given, students, we have given a circle with radius O, and let PQ be the tangent and AB, A be the point of what? Point of what, students? Point of contact. Right? This is we have provided with. Okay. Now, what we have to prove? We have to prove that OA is perpendicular to what? PQ. Okay, if we prove this, the theorem will be proven. Okay. Now the proof. I'm doing a construction in this. What is the construction? I am having a point on this line PQ. Let it be here in this side. Right? Now I'll need that. These points. Let it call B. Okay. So I'm having this triangle OBA. Right? Okay. So here I will have a construction. From construction, what I will have, this is the way we prove a theorem. We will be writing the given things, then we have what we have to prove thing, and then the construction thing, and then the proof afterwards. Okay, this is the sequence. Right. Now construction. Draw a point, what we have taken? B on tangent. What's a tangent? PQ. Okay. Now, this is a tangent. So, I cannot be able to draw this point inside this circle. If I'll draw this point inside, that means what? This is secant, not a tangent. So, obviously, this will be the outside point only. Okay. Now, this is what we have constructed. Now, the proof comes. In triangle OAB, OB is equals to, if this is R, radius R, and so this will also be, this point let it call B dash. So if OA dash is R, then this will be again R because radius will be same here. Okay. So OB equals to what? OB dash plus B dash B. Right. That is equals to R plus B dash B. This is one. Now second, this OA is equals to R. Now this is the second. Now by 1 and 2, I can say that this is R and this is R plus something. So R plus something, something plus something. Okay, something plus something more will be always greater than what? Something. So this OA will be always lesser than this R and B dash B. So from 1 and 2, we can say that OA is less than OB. Right, students? Now, I will do what? I will have this point B here also, here also, here also, and here also. What will I found? What will I find? That each and every time this length will be what? Greater than this. Now, if I shift this point to this side, the same will occur. At this point, this side will be what? Greater than this side. if I take point this thing here and here, I will observe the same thing. So, whenever you are going to take this side will always be greater than this OA. So, what I found that OA is the what? Shortest side possible on this tangent, right? And the shortest side possible is what? The perpendicular, right? So, we have proven it. So, just write it. Now, by having points on either sides of A, I am rubbing this given portion, right? So, now by having points on either side of A, we see that OA is the shortest side possible on tangent. What was our tangent? PQ, right? This implies what? That this OA is perpendicular to this PQ. Or I can just write it like this. So, students proved. You have proved this. Now, note this. Okay, I am rubbing this. Okay, students. This is one thing we have proven, and we have collected enough information about circle to have some questions on it. Okay, so here's the exercise. How many tangents can a circle have? How many tangents can a circle have? Okay, I have told you in my first lecture, if you can remind it. Okay, so I am having a circle here. I am having this circle here. Okay, that's saying how many tangents. Now, I can have that point and draw a line. Okay, and that will be the tangent of the circle. Now, I will be having this point and will draw, and I will be having this point. I will draw tangent. I will draw tangent. I will draw tangent and a tangent and one more and one more and one more and one more, and this process continues. That means each and every point of this circle can have a tangent, and a circle is consist of what, students? Infinite number of points. That means it can have many or infinite number of tangents. So, what I will write here? Many or infinite? Infinite. Simple. Okay. A tangent to a circle intersects it in points. What? A tangent, let's suppose it's a tangent, points, it's intersecting 1 here, 1. What we concluded? That only 1 point. So, I'll write 1 point here. Okay. Now, a line intersecting a circle in 2 points is called it's talking about a line, not a line segment. So, it will be secant. This is a circle, and if a line crosses it, intersecting it 2 points, A, B or PQ, let's say. So, what will be calling it? It will be called as secant. Okay. A circle can have parallel tangent at the most. I have repeated it so many times in my lecture, so it's very clear. We'll be having what? At most 2 parallel tangents. Okay. Like this is the circle. If I am having a tangent here, only one tangent can be drawn parallel to it. Okay, and these tangents will be parallel lines, right? So, the common point of a tangent to a circle. The common point to a tangent circle, that means at the point where the tangent touches the circle. What we call it? The point of contact, right? The point of contact. Right, students? Now, draw a circle with two lines parallel to a given line such that one is tangent and the other is second to the circle. Now, we can do it like this is our circle. Let's suppose it's a complete circle, Okay. Now, it's saying draw a circle and two lines parallel to a given line. So, I am having a given line here. So, it's telling me to draw two lines. Which two lines? Parallel to given lines is that one in tangent. So, I have to draw one tangent. So, my line should be parallel to it. So, parallel to it, I will construct here. We know how to construct parallel lines, right? Okay. Now, the second is what? One which intersects at 2. So, these will be two parallel lines, one at this point of contact and the other above that. Okay. Any doubts about that? You can draw it here, you can draw it here, anywhere, but not outside the circle or on the circle. This one for the second. Okay. So, we are done with this. We are done with this exercise, students. Yes or no? Okay. Now, a tangent PQ at a point P of a circle of radius 5 cm. Okay. So, what we are having? We are having a circle, right? We are having the radius 5 cm and tangent PQ. So, this is tangent P and Q, right? Radius 5 cm meets a line through the center O. Center is O at a point Q such that, so we are having this point O that meets this point Q, and we call it as here P. So, that OQ, now this is OQ is equals to what? 12 centimeters length of PQ. This is 12 centimeter. So, it's telling me, it's letting me length of PQ, right? Now, PQ is it? Tangent PQ at a point P. So, it's having a point P of a circle, right? So, P is not here, but PQ is there, here. We are having it here, right? A tangent PQ at a circle of radius 5. This is 5, this is radius. So, we have to find PQ's length. So, it's so obvious. We can have this right angle triangle. We have proved by our theorem that that will be 90 degree. Okay. The angle between the tangent and this radius, right? So, we can have the Pythagoras theorem here. So, we can simply solve it like 12 square will be equals to 5 square plus whatever QP square or PQ square will say. So, this is 144 minus 25 equals to PQ square. Now, you will be having this PQ square equals to what? 911. Okay. So, PQ will be what? Root 119. So, this will be your what? Answer. Now, see the options. You are having here the D option. Okay. So, it was easy, right? So, can I rub this now? Okay. Okay, students. Now we'll be discussing next the number of tangents from a point inside a circle. Right, students? So, number of tangents from a point inside a circle. If I take a point inside circle, that means what? This is my circle, student. If you are not able to visualize it clearly, I'll darken it for you. So, this is my circle. And I'm having a point. A point is like this, but for you, I'm making it some larger so that you can clearly see it. So, it is like this dot, but I am making it like this. So, number of tangents from a point inside a circle. Now, if I draw any line from here, any, okay, you'll try and you'll see that if you try to draw any tangent here, it will what? If you extend this here, I'll be extending it with another chalk. If I'm extending this line, it will get cut this at 2 points. If I'm extending this line, it will be cutting it at 2 points, and any other line you will be having, if you extend it, it will be cutting it at 2 points, and this is prohibited for our tangents. So, number of tangents from a point inside a circle is what? 0, right? So, we can write it like 0. 0 number of tangents. No tangents at all if the point is inside the circle. Okay. This is one case. So, what case is next case? Next case is when the point is on the circle or on the circumference. If the point is on the circumference, okay, so I can be having only this line. This line is not looking the one. Okay. So, I can have what? Only one, let it call PQ. PQ is family of tangent. So, we will draw PQ here. Now, we are having only one tangent from a point if it is on the circumference, right? Mark these words. If it's inside, we'll be having no tangent from this point. If it's on the boundary, that means on the circumference, we'll be having only one tangent. And the next thing is, if you are taking count for inside, you will be taking count for outside too. Okay. So, let's see what happens when it have its point outside. So, in this case, I'll be having this circle and a point here. Now, from this point, I can draw a tangent this side, students. I'll call it point, what we call P, and this point as T1, not this point. I'll mark it here, T1. Okay. Now, the next one here, and I will call it as T2. So, from here, it's clear to say that if you are having, now can you draw any other kind of tangent here? Like I draw this 2. Can you have some more tangents here? No, you can't. So, maximum of 2 if the point is outside. So, for inside, you're having 0 numbers. For at circumference or on the circumference, you are having 1 tangent, and if it is outside, then you'll be having 2 tangents, right? Okay, students. So, we have some interesting thing about this P2 and PT1. PT2 and PT1. I am calling this tangent because it's tangent. I am writing the word T here. Okay. Now, this is a point, so I am calling it as P. Okay. So, I am having these 2 tangents PT1 and PT2. And you know what, students? These 2 tangents are exactly equal. We'll be going to prove that also in later session. Okay. So, what is of your use now that we are having this P2, T2 and PT1, and somehow we are having this PT1 equals to PT2, and we are going to prove it also. Okay. So, PT1, PT2 equals to what? They are called as length of the tangent from the point P. I have drawn this much line. This is extended version. There PT1 is, it's extending. Okay, beyond T1 is extending. But the length of tangent is what? Length of tangent is only from P to T1. Like this, here, it's only from P to T2. You will not count the length of tangent from P to this line because this is a ray and this will go infinite. Okay. So, this is the length of the tangent from the point P to the circle, right? Also, PT1 equals to PT2, right? Now, next is what? We are having a theorem. So, we have to prove this theorem. The theorem is the length of tangent drawn from an external point to a circle are equal. So, what I have told you in the previous thing, here you have to prove it there. So, you have to prove this. Now, you will use the first theorem. Now, what was the first theorem? That if you are having a tangent and the radius here from the point of contact, then these two will be perpendicular. And now you will use that theorem to prove this theorem. So, there is a theorem sequence and you have to remind it, you have to remember all that in your mind to prove the next other theorem. Okay, students. So, for today, it's, it's sufficient to have a lecture here, cut here. In our next session, we are going to talk about this theorem and will do some exercise and questions, right, students? Till then, take care. Thank you.